Thank you for the invitation, and thank you for this kind introduction, also for reading out the title for today's presentation. So I will point a little bit to features that I believe we know better, and later also to some things that we don't know that well. But I want to start with advertising Mainz. So I'm from the University of Mainz, and we are now a couple of groups there and believe that we represent a center for terrestrial proxy archives. Many of them were mentioned already now in the talk by Edouard. So with the group of Gerald Haug, who will give a presentation later and also gave me this tool now, we now have a big group looking into ocean sediments. So this clearly has international visibility. There are other groups looking into lake sediments in Mainz. That is a group of Professor Sirocco. We have a group, and that was also mentioned by you, the stalagmites, looking into the speleothems in Mainz. That is a group of Dennis Scholz. And then a group looking at sclerochronology, like the mollusks, for example, and then my group looking at dendrochronology. And as was already said, that is one of the prime proxies, if not the dominating proxy for the last millennium, because it has annual resolution. It can be calibrated against instrumental temperature data, but also other instrumental data, and then be transferred into absolute temperatures. And it is available at large spatial scales. So outside the tropics and the polar region, you can apply tree ring research. Now for today, I would like to give you first a crash course in dendroclimatology. So very briefly outline some basics to understand how this works. And then there are these two examples. One is looking in what you call the Couvé eruption. I'm not using this anymore because the geologists keep telling me it might not have been Couvé. So it's about the dating of this really major event of the last 1,000 years. And then the third part of the talk is about last millennium temperatures and to look at some of the underlying data that we have available for that period. All with a focus on tree rings, obviously. So let's start with the crash course. This is a single ring of a conifer. So here's winter, then the cambium, that is the tissue that can divide and produce cells, is starting and produces this early wood from here to here. So these are cells that are large in size, and the cell walls are thin. And then after some weeks, so this is happening now, and then during high summer, the cell production slows down. The trees invest more of their money, of their energy into cell wall growth, so the cell walls become thicker, and these cells are also tangentially compressed, so they are a little bit compressed in this direction. And this would then make up the late wood. So this is the early wood, and this is the late wood for conifers. And the most easy and most widely applied parameter or proxy is the tree ring width. So you measure the distance from here to here for each ring. There are also other tools, like this graph here shows a high resolution density profile. This can be produced using X-ray technology. This is something we have ready in Mainz. And then this X-ray curve, you can use these points here, the lowest and the highest points, and especially this highest point here, the maximum late wood density, is a good proxy, if not the best proxy out there, to estimate summer temperature variability. It's an approximation of the thickest cell wall in one of these last cells here. And this cell wall growth is a sum or is influenced by summer temperatures. Yeah, there are other features. I'm not going into detail today. That doesn't work everywhere. You have to go into boundary sites. That was also already mentioned. So here's an example from the Tian Shan in this case. The upper tree line is in 3,200 meters, so approximately 1,000 meters above the tree line in the Alps. If you go there, then you get this picture here. So lots of rings, maybe 30 or 20 rings on that picture, in comparison to the rings from the valley bottom, for example, here, and then you have only 3 rings visible at the same distance. So growth is slowed down near the boundary, And the variability from year to year is dominated by temperature. Because this upper tree line is there because above it is too cold for trees to grow. And that's why a single factor starts dominating the variability from year to year. Whereas here you have many factors, including drought, the forester, the insects, and other effects that cause the changes from year to year, or influence the changes from year to year. So if we go to a dry environment, here from the Atlas Mountains in Morocco, the same applies. So here we have these beautiful Cedrus atlantica trees, these big trees. So there's a person standing here, and they go back 1,000 years. And you can use this to reconstruct what we call the Palmer Drought Severity Index. That is an index derived from temperature and precipitation and some soil data. It's a drought index. That is shown here. That's from the instrumental data for February to June. And then yellow, these are the ring width from these big trees. And you can then use these ring width to approximate the PDSI values and use then a statistical relationship from there to reconstruct PDSI over the last 1,000 years. So you go into a dry environment to reconstruct drought, and you go to cold environments to reconstruct temperatures. What applies to the upper tree line also works for the northern tree line. So here we are at the Taimyr half island up there. This is the place where you find the trees, the northernmost trees on our planet. So this is at 72 degrees north. It's also a beautiful site. Here you get the tree line is made up by Larix Siberia, and of course this is also a site where the trees are sensitive to temperature variability. So the first, so to say, take-home message would be to visit tree line sites to minimize the number of forcing factors and increase common variance. So what is meant with common variance? Let me outline this. Going back to Central Asia, to the Karakoram Mountains. So here we are at the upper tree line. The upper tree line here is actually at almost 4,300 meters, so it's fairly high. You have to be a young person to go up there. At least I can't go there anymore, I guess. The trees are very old if you go up there, so not very tall trees, only 4 or 5 meters tall. These are juniper trees, and they reach very old ages. So this tree goes back to 826 after Christ. If you sample many of these trees, like 15 or 20 in that picture, and we look at the ring width data, the tree ring width data for the 20th century, then this is the picture you get from 15 single trees from this environment. And at first glance, you see that there is common variability. So all trees have a narrow ring in 1911 compared to the years before and after. And there are other years like this, but there are also periods, like here, or single years, where some trees have a wider ring and other trees have a narrow ring. And that is what I call the changing quality through time. I guess that is the case for all proxies, for all archives. For the trees, you can see it very clearly. So this is a high quality period, this is a low quality period. You see common variability from year to year, and in this case also at this decadal scale. So this is maybe a multi-decadal thing. The trees become wider and more narrow, and all trees, or almost all trees, do that. So common variance at interannual to decadal scale is what this picture shows. Yeah, the mean of many of these trees is called a chronology, and what we then typically do to continue with the crash course, so this is the proxy, this is the chronology, the mean of many tree rings, and then we compare this during the period of overlap with instrumental data. And then we can do a lot of statistics. I'm not going into detail here. Convince yourself and maybe your readers or listeners that there is a good statistical relationship, that it is temporally stable, and then use this relationship to reconstruct temperatures over the pre-instrumental period. This is what we do typically in dendroclimatology. Now here's an application. We look at a lot of tree ring chronologies from Europe, and what is shown is the correlation with June, July, August temperatures, so the summer temperature signal. And then you see that there are positive correlations. So the reddish colors are in Northern Europe, some in the Northern UK. Here are the Alps, and this is the Tatra. So if you go cold, you get a temperature signal. And if you're a little optimistic, I would say, you would also perhaps see that you get more bluish colors if you go to the Mediterranean. This is the inverse signal, so this is a negative correlation. In most places in Europe, during summer, the temperature is anti-correlated with the precipitation. So if it's a cold summer, it's also a rainy summer. And this is what is shown here. So these are actually drought signals that are now shown here as negative correlations with summer temperature. That's why they pop up. But it's not as clear as the red colors, obviously. So how can we cover the last 1,000 or 2,000 years in Europe? It's possible in northern Greece. So this is the oldest tree in Europe. We found it in 2016, and it made it into CNN. So that's big news. We gave it a name. It's Adonis. It's in German a Panzerkiefer, a Pinus heldreichii, in about 2,400 meters in northern Greece in the Pindus Mountains. And it has a continuous, so you can measure the rings for the last 1,075 years. So there's one tree older than 1,000 years that you can look at the rings. There are many trees that are older than 1,000 years, but it's also based on belief, because these trees are hollow. They are rotten inside. So these are not really countable for us. So this is the oldest tree, and last week I was in Corsica, and just because this is a talk in France, I thought I should show that. So you also have very old trees here. So these trees are 800, some of them are almost 900 years. This is Pinus nigra in this case, and there's lots of dead wood on the ground, and that's why we were there. So we were there with the chainsaws to collect this material from the ground, to hopefully connect these trees with this material. The technique that we apply here is called cross-dating. And here's a graph that is often shown. So here's the living tree, and let's say this is a sample from a building, or this is a sample maybe from Corsica taken with a chainsaw. And if there is common variance and overlap, obviously, between these trees, so if they're too old, then it doesn't work. But if there's overlap with living trees, then you can use this common variance to cross-date this sample on that sample. So in this case, you then go further back in time, and with this technique, we can address periods that are much longer than the age of the trees. So if the age is only 200 years, and we use this technique, and we have the samples at hand from old buildings, for example, we can go back 1,000 years or 2,000 years. So common variance is the key for cross-dating and the development of climate reconstructions. Only if you have common variance, if many trees do the same thing, then you can reconstruct the climate. If the tree rings do different, or the trees do behave differently, then move on and go somewhere else. Here's an application. So we are now in Lapland. The situation is slightly different. Here are the trees right next to these lakes. They're very shallow, and you can see the wood in the lakes. So this is what we take out. The trees are preserved in the lakes for up to 7,000 years in perfect shape. And then we combine these trees with these trees using the cross-dating technique. We measured the tree ring density. So in black, you see about 100 trees, and the maximum late wood density is measured. The chronology is the red curve. So this is the mean of all the single trees. These are the black curves. And you see the first 10 years of instrumental data. This is the blue curve. And Edouard already pointed to that. So the early instrumental data are not very trustworthy. And we also look into this there, doing urban climatology in the region. So I would say that the red curve is actually a better reading of temperatures than the blue curve. But be it as it may, here's the picture for the last 120 years. So we looked at this first 10 years. This is the early instrumental period, and here you can now compare the tree rings, the density chronology, with the summer temperatures over this longer time period. convince yourself that this is a stable relationship, and then use this to reconstruct climate over the last 2,000 years. So this is the longest maximum latewood density chronology that is developed so far for the last 2,000 years. And now I can point to some of the features that were shown earlier. So this is the Roman warm period, 2,000 years ago. This is in Northern Europe. We are in Lapland, in Finland. This is the medial warm period. This is recent warming. It doesn't go until 2018, so this is cut off earlier. And then there's this period that was called the Dark Ages, or the Great Migration Period, and we like to coin the term, the Late Antique Little Ice Age, the La Lila. Maybe that's too complicated, but let's see. And this would be in, the Little Ice Age that was mentioned earlier. It's fairly extended and slightly flat in that region. So with this, I hope you got the basics on tree ring research, and I would apply now the method with this, with the 1450s eruption. Let's start with the satellite era. So that starts at 1979, and if you look at the temperatures at global scale, so these are satellite-derived data, and it was clearly explained that the Mount Pinatubo eruption is very important because that is the eruption that occurred during the satellite period. And you could study very well the climatic impact from that. And Edouard also said that there's cooling following this eruption that happened in June 1991, and here you see this cooling pattern at a global scale from the satellite data. What you also see is that there are other coolings, like here, here, and somewhere else, that are obviously not forced by a large volcanic eruption. And only from that picture, it is clear that it makes sense to reconstruct climate over the last 1,000 or 2,000 years at annual precision to study more than one volcanic eruption to see what is the typical cooling that you get after volcanic eruption, because there are lots of unforced or naturally forced or differently forced variability that looks similar. So there was already mention on the Mount Pinatubo eruption. It was in June, actually, and it has a size of more than 11 billion square meter of tephra. That makes it a VEI index 6 events. A volcanic explosivity index 6 is reached above 10 billion square meters. Yeah, and also this was shown, so you have to, these eruptions inject into the stratosphere, the dry part of the atmosphere above the troposphere, so you have to, the eruption have to be that strong that the aerosols are making it into the stratosphere. The stratosphere here in Paris is about 12 kilometers high. And there is then the global distribution, and there's the cooling there's warming in the stratosphere and cooling at the surface, and this is the signal we try to catch with the trees, obviously. I'm also showing this graph again. So here in the top there's the volcanic forcing, and one of these spikes here is the one of interest in the 1450s. And as you talked already about this, so I move on and I don't have to repeat all that. You also explained how the aerosols are distributed, and then they're making their way into the ice cores and on both poles, like Greenland and in Antarctica. And this is the archive that is giving us these time series up there. And up till some years ago, one of the key papers that was used by the modelers and by many people was Gao et al. They combined 33 ice cores from both poles, and they had a major event in 1452. So that's a minus 12.3 watt per square meter event. It's one of these big spikes in the last 1,000 years. And then there was this newer paper that you also showed, that is by Siegel et al. There are several papers now. They used new ice cores. The event became even stronger, and it was shifted by 6 years. And this is what I want to look at now. is this shift, is it supported by the cooling? Is it supported by the tree-ring evidence? So there is kind of a conflict here between these two papers, and this is now the data set that I guess will be used by lots of models in the future, also in the upcoming IPCC report. So it's kind of interesting and important to get the dating right, because otherwise it will affect the models that then show cooling in a different year than we find it maybe in the proxies. So that is the little example, this little paper that I'm now going to show. So we use the maximum labeled density data from NSCAN. So here's again this example that I showed earlier. So this is the data from Lapland. Here's the picture. And what we did in this little paper is we then correlated the temperature, the tree ring density from the site with a global data set of summer temperature. And then hopefully around your tree site there is a red spot. And this is what we find. So there is these trees are influenced by summer temperature in the region. You also see other patterns somewhere else. Some of them, I don't go into detail here, some of them are tele-connected with the pattern that you see. Some of this is also randomly popping up. This is because you correlate lots of grid points globally, and you only have a data overlap of 100 years between the trees and the summer temperatures, and then naturally you should get some random patterns if you do this for the northern hemisphere. But hopefully where the arrow is, there is a red dot. So we now do that for all MXD chronologies that reach back into this critical period for the 1450s. So that we did this with a team of dendrochronologists, dig into the archives, and then what we found is 20 density chronologies that would cover that critical period of the 1450s. These are actually all density chronologies in the world that are available. And there are no data, obviously, from the southern hemisphere. So if you have time and motivation to develop a density record for example, for Patagonia or in Tasmania, where all trees are available, that would be helpful. So it's only available for the northern hemisphere. Here is the NSCAN site, and you see the same pattern, and then hopefully we can go a little bit, I want to tell you where the sites are. So they're in the Alps, in Pyrenees, there's one of the sites, then several sites in northern Europe, in central Sweden is a site, then in some sites in Siberia, a new one now in the Altai, and there's another one coming up now. There are sites in the Rocky Mountains up to Alaska, and one is available in Quebec. So this is where the data is located. So it's not really full coverage of the northern hemisphere, obviously, but this is as good as we can make it. So now I just want to show you the reconstructed summer temperatures. So these are temperature anomalies with respect to the climatology in the 20th century, and we zoom into the period from 1420 to 1480. And at the next picture, you get the result of this study. So these are the 20 chronologies, the 20 reconstructions, and except for one located in Athabasca, they all show a distinct cooling in the year 1453. So this is the cumulative effect from what you see on top. And if you compare with the years before and after, this is the only really distinct cooling event in that period of interest. In particular, the years 1459 or 1460, that would be following the eruption or possible eruption in 1458, are not really sticking out. So that's the result. It's a very brief paper. You can also put now these patterns in space and look into this. So this is the Athabasca site. This is the only record. This is from British Columbia. That doesn't show cooling. I'm not fully sure why that is the case. Maybe it is real. A good friend of mine produced the data, so I blame him now, but I'm not telling you the name now. If you want, you can then look in a little bit more in detail. Most of the cooling, the strongest cooling is in Northern Europe and into Western Siberia and also here in Alaska, for example. If you take all these sites and make a network mean, this is the mean that can go, it's reasonably well back to 1200. Before then, we have too many sites dropping out. They are shorter than the NSCAN record. And if you do that, then it's interesting, you see these single spikes that are coming out here, and this is 1453, so I put them now on. So here, this is Couvé, but again, the geologists don't like to call it Couvé anymore. I don't care. It is a big eruption. And in terms of cooling, it is the biggest event of the last 800 years, and we know before it was silent, so that's likely the biggest cooling from a volcanic eruption of the last 1,000 years. And it happened in 1453. And what I named out now here are the 9 coolest, the 9 most negative spikes on that graph. And if you do that, and now I have to read this a little bit, then most of these, except for one, this one, 8 of these are related to volcanic eruptions. So clearly, this strong cooling at large spatial scales are caused by volcanic eruptions. This event here in 1346 is an unknown event, so we find evidence in the ice cores, so it's likely a tropical eruption, but it's not known where it is. Then the summer of 1699, that is the only one that is not related to a volcanic eruption, and it is fairly recent, so I guess we would know if there would have been a volcanic eruption. That seems to be naturally forced. It seems to be unrelated to volcanic eruption. And there's only one cold summer that is related to the Lucky eruption here. That is a non-tropical eruption, so it's located in the northern hemisphere. And that's also the only one where the eruption is then occurring in the same year as we find the cooling pattern. When there's a tropical eruption, you have the eruption, and in the following year, you see the cooling on the northern hemisphere. That's true for all other events, except for Lucky, then it is in the same year, obviously. So that shows that, shows 2 things. One is volcanic eruptions are important, and it also shows that using such data, obviously the tree rings contain a clear signal in the high frequency domain. But this is not really showing anything about low frequency, so no little ice age, medieval warm period, and recent warming. That is all taken out. These data are optimized to look into these cooling events at decadal or at annual scale. So tree rings can be used to reconstruct post-volcanic cooling. I would hope that you take this message home. And second, the original dating of the of the Couvé eruption was correct, at least. I mean, in the paper we say, we don't word it this way, we say there was cooling in 1453, which points to a volcanic eruption in the year before, but it's also possible that there was a volcanic eruption later, but that had no climatic effect, no substantial climatic effect. Okay, then go to the third part of the presentation, to the last millennium temperatures. So here again you see one of the core samples and the nice rings. It's a core sample that hit the pith, the center of the tree, as a good sample. And I want to first go a little bit through the papers that showed this northern hemisphere temperatures over the last 20 years. So we look at a large spatial scale, northern hemisphere. The first paper was produced by Briffer and colleagues in 2000, published in QSR, and it combines only a limited number of site chronologies that are fairly far in the north, between 45 and 72 degrees north. This is the curve. The next paper, only using tree rings, was then produced by me and a number of colleagues that already combines 14 sites over the northern hemisphere, and it also reuses lots of the data that was used by Briffer, obviously, so there's data overlap between the curves. Next one was then 4 years later by Rosenda Rigo and colleagues. The network is expanding a lot, many more sites, and you see it looks fairly the same. Now there is a time step, so now I would say this is state of the art now. These are older records, and now these are state of the art records in the next 3. This is a publication by Lea Schneider and colleagues, only using density, fairly similar. Here's a difference in the 14th century. So Schneider paper that shows warmer temperatures in the middle of the second millennium. Then there's a record by Stoffel et al., again using many more data. It's shown here in gray, and the latest is a paper we produced just and published very recently, again in QSR. And here you see the network. It's even now expanding very well into Central Asia. And yeah, but many of these records look very much the same. And things that were already said earlier by Edouard are these common features. So the medial warm period, that seems to be important. The little ice age, it's not clear when it really starts, especially if you use the new record by Schneider et al. And then there's the recent warming, and again, the most recent years are truncated here because many of the rings of the chronologies were sampled in the 1980s and 1990s, so we can't show the 2010s here. And what these papers do is they also show quite a lot of statistics. I'm showing just one here, that's the R-square statistic. So this is the correlation or the explained variance between the tree rings and the instrumental data during the 20th century. And this is using what is called a nested approach. So the, maybe it's too complicated to very briefly explain that. That is showing that there is a decay in signal back in time. So the signal is stronger, or is better represented in the 20th century, in the 18th century, and then there's a slight decay back in time related to all of these reconstructions. Now I want to look in more detail into these sorts of statistics, but I want to show you real data. And for that, I'm using graphs from this publication here. So this is a group effort that actually took more than 2 years to put this together. So it's a paper where we rank the tree ring-based temperature reconstructions of the past millennium. So we are now in the period of ranking. The universities are ranked, everything is ranked. So now we rank the tree ring chronologies in that paper. And it's actually, it's an online source. So if there is a new 1,000-year record, it is now added and will be ranked with the others. So, and I will only focus on 3 points. One is replication, age, the second is age, and then the third is signal. So first, let's have a look at replication. So how many chronologies are available and how many trees are available for the last 1,000 years. This is the picture showing all 1,000-year reconstructions from tree rings. You see there are many in Europe, in Asia, in North America, and only a few. These are actually only 4 for the southern hemisphere. And you see how these records correlate with each other. That's a fairly noisy picture. And these are just the records as they were taken out of the literature. So they were not rescaled. So some of them had a lot of variants, and some have very few, very tiny variants, just as originally published, all plotted together. This is the locations. You see again here in the Rocky Mountains are sites. This is a Quebec site. It's a little bit like the MXD network I showed you earlier. There are more sites from Central Asia. There's one from Chile, one from Argentina, from Tasmania, and from New Zealand. These are the 4 sites extending over the last 1,000 years. This is not only density, this is ring width mostly. So these networks go further back in time. Yeah, the Alps, this is the Karakoram, this is Altai, and this is Central China here in the Himalayas. So we have only 39 records extending back to 1,000. It's actually 40 now, because just last year, or this spring, a new record was published. 49 in Asia, 13 in Europe, 8 in North America, and 4 on the southern hemisphere. It's not a lot. It's not 400. There are 400. There are thousands of tree ring records, but there are only 40 that have a temperature signal, and it go back over the last 1,000 years. So there are only a few annually resolved and absolutely dated reconstructions back to 1,000. Annually resolved and absolutely dated, this is the only archive that can do that. Right? So you already noticed that with the ice cores, there are some missing layers. So if you really want to have annual dating control over the full millennium, it's the tree rings and a few documentary records. Jörg Lutherbacher would know better about that. So I want to stick with replication. What is the underlying data? I go back to this site in Greece that we are now working on with Adonis, and here see what we already measured. So we measured 400 trees. Each bar represents a single tree, and this long bar here from 1000 all the way to the present, this is Adonis. This is the oldest tree in Europe. And this is how it looks. So many trees are younger, and then we also find deadwood on the ground and use this, and with this deadwood on the ground, we extend now the chronology back to 600 AD using the cross-dating technique. And what you also see in that picture is that there's always one single tree, in this case it's 2 cores from one tree, that is the oldest. So replication is 1 here, and replication is a lot now. So we always have an increase in replication from the past to the present. That's very typical for our proxy. So now we look at these curves. This is a replication curve for one of these dots in our library. This is from the Central Alps. It's one of the green dots here. And you see it's very well replicated. It's 300 series in the 20th century. It's fewer back in time, but still 80 series or so 1,000 years ago. That's the replication curve of one of the 39 or 40 records I showed you earlier. And here, this is made up of living trees here, plus wood from these historical buildings in the Swiss Alps, for example. And this is actually one of the oldest buildings in the Lötschental. The oldest building in Lötschental dates back to 1302. It has 300 rings, and with this you can then cover the last 1,000 years. Another example is Tornetresk. That's an MXD record. That is a ring width. Most of these records are ring width. Tornetresk has an MXD record. And you see the replication is really tiny. It's about 60 up here, and then it declines to below 10 in the 11th century. It's really not a lot. This is this area here. It's an older record that was produced earlier. And that's the record that is used in every large-scale reconstruction that I showed you earlier. So the original version was published in 1988. It's a very important record because it's in all of the reconstructions, but it has only a few data if you go back in time. A few trees. So here's the picture for Europe. All these 13 or 14 records from Europe. These are the single replication curves, and then red is the mean. And you see we have lots of trees in the 20th century, and we have a few trees in the 11th century. That is an important key characteristic of dendrochronology. So there are only a few absolutely dated and unresolved reconstructions back to 1000, and many of these contain a few trees only during medieval times. That's important to know. So let's think about replication plus the calibration. I show this again. This is the replication for Europe of these records. This is the picture I showed earlier for the Lapland example. And so it's obvious that we do the calibration always in the 20th century, sometimes 120 years, a little bit more, often less. And that's a very optimistic approach, isn't it? So we always calibrate, use the chronology and compare with instrumental data when there are lots of trees behind the chronology. And if you think about this, so let's say this is a 1,000-year, it's an artificial data set in this case, but let's say this is a 1,000-year reconstruction, then obviously this is a German word for uncertainty. The uncertainty is not like that. The uncertainty should be like this. The uncertainty should increase because you have fewer trees back in time. The uncertainty has to increase back in time. That is very challenging to statistically cover that, because it's not only the number of trees, it's also the common variance between the trees that changes through time. It's also the age, another effect that I will show in the next step. And that is very difficult to capture on a single site basis. It's almost impossible to capture this sort of noise, increasing noise back in time, at the hemispheric scale. Let me show you another example, age. So I go back to this tree here, the Adonis, and this collection that we're now working on, Adonis now is 1,075 years old today. And it was 1 year old here, right? So it's aging. It's really an old guy. And that's true for all of these trees. So all individual trees are old now, and they're younger here. So the age is high in the 20th century, the mean age of this collection, and it decreases back in time. However, if there is a dead tree here, that is relatively young. Maybe this is only 100 years old at this time. So if you find relict wood on the ground, then the age all of a sudden drops, because you include younger pieces that are lying around or covered or from the lakes that are preserved there for centuries. So this is making what we are now looking at are mean age curves. So here's a fairly monotonic increase of the mean age curve in Dulan. That is one of the points here. And why is that? This is because there are very old trees in the region. So these are the juniper trees in Central Asia. These are these twisted trees. Here you see one of the trees. The center is here. The tree grew like a regular tree for the first 300 years, and then for the last 700 years it grew only in one direction. The bark is stripped off. There was a strip piece of the bark here, and we call these trees strip bark trees, growing only in one direction. Very typical for Central Asia and that species. Because we have these very old trees reaching 1,000 years, 1,500 years, and this chronology, the Dulan chronology, is made only up of these very old trees. We have an age of almost 600 or more today, and it's monotonically decreasing back in time. Okay. A very different example is the Polar Ural. That's a fantastic site. I really can recommend visiting that. From several perspectives, it's interesting. So here you see the colleagues, the Russian colleagues working on this. Stepan Chiatov is the key person. And what here is, the trees are fairly young. They're only 200 years old. And then these 200-year-old trees are combined with many, many other trees back in time. These in situ trees here that you find, but then also many trees that are sticking out of the sediment. And if you do that, then you result with this absolutely flat age curve. Because every time you go back in time, and every time there's a new piece that is added to the collection, then the age goes down again. That is good, that is bad. Just from the age perspective. That's also good data, but it has a tendency in age. Now let's have a look at the full data set. This is the mean age curve for Asia, and I'm not fully sure what's happening. So this is the age curve for Asia. That's the age curve for Europe. It's much more flat. That is because we have many chronologies, like from the Alps, where we combine very short living trees with samples from these old buildings or from the lakes. That's why the curves are more flat here. The oldest trees are in North America. We heard about the bristlecone pines that reach ages of 4,000–5,000 years. That's why here we have the biggest problem with age. And I'm now taking an excuse. I don't tell you why it is difficult. I just point to the literature. So there are papers like this: Climate Signal Age Effects, Evidence from Young and Old Trees in the Swiss Engadine. So it's an older paper by us, but this term is now used a lot: Climate Signal Age Effects. We know that the climate signal changes when the trees are young in comparison to old trees. It's like with us. It's like with me now. I go jogging and the next day I feel really bad. And it's the same with the trees. So the effects of climate on the trees changes with aging. And that is actually, that is problematic. Now we calibrate. So calibration is done against too many and too old tree rings in the 20th century. And obviously, again, statistically, this is very difficult to tackle. Let's quickly look at the third point I want to make: signal. Signal is effectively the correlation with instrumental data. It's more, but for today's presentation, and for this ranking paper, that's what we looked at. So here's one of these ranking tables, only the top part. It's very complicated. That's why I zoom in the next graph. I'll show you the whole thing. So here you see the length. This is the overlap of the records with the instruments. So here's the Tornatress record. I said this is used in all of the reconstruction. That's the MXD version of it. It has 147 years of overlap with instrumental data. It correlates absolutely fantastically, 0.484. And the difference between calibration and verification is very small, and this is something else. And it gets a green sign, so it's a very good record in terms of signal. It's a very bad record in terms of replication. You remember, it had less than 10 trees in the 11th century. And it has lots of trees, 60 or 70 trees in the 20th century, and this is the result from correlating the mean of 60 or 70 trees, not 10 trees. Okay, so this is the full picture. And here you see all these numbers. There's no point now in going through that list. I just want to pick one from, so these are the good ones are green, and the bad ones are here in blue. I produced some of these records. Now for example, take the Karakoram record. So this is this one there. Then, where is it again? Karakoram. So the correlation is 0.31 over 115 years. There are reasons for that, because one reason is that the tree rings, the tree site is in 4,200 meters, and the meteorological station is at 1,300 meters. So it's not really representative of the high elevation. But this is also, that's a big problem for precipitation, less so for temperature. But still, it's a problem. The point is, it only correlates at 0.31 over this 115 years, summer temperature versus the tree chronology. And look at some of the other numbers, especially in the lower part here, or at the differences between calibration and verification. That's not very stable in time. So the point I want to make here is that we calibrate against too many and too old tree rings, and still the explained variance, the temperature or the instrumental temperature is typically below 50%. So half of the variability, or much more of the variability in the chronologies, is not related to temperature, at least not to the one that we record with thermometers. There's lots of noise in the data still. There were many negative points. I want to make a positive one now before I then conclude. I go back to this very noisy picture. So we only took the data as we got them out of the literature and plotted them on top. This is the same data. So the red curves here, 1, 2, 3, 4, have now different colors for the different continents. So these are not really continental means. These are just the mean of these single black curves on the previous graph. We know the southern hemisphere has only 4 sites. So I take this away. Well, that looks good, doesn't it? At least to me. When I saw that, I was really surprised. We just took the data, made continental means, plot them on top. You see here the Cuvée eruption and the aftermath. There's lots of biological memory in that period. But then there's common variance everywhere. The correlations between these simple mean curves are 0.56 between Europe and Asia. Asia, North America, Europe, and North America. These are correlations over 1,000 years. Right? So there is signal, something positive. So you can use these data to reconstruct climate, but you also have to keep in mind that the replication is low, that the replication changes, that the trees are aging synchronously, and that the explained variance is less than 50% in most of the cases. Preserving long-term cooling trends is challenging, so I don't go into detail with this. Just very briefly, this is again the hockey stick that was shown earlier, the red curve, and this is from the 2002 paper. And the point that we made at this time is that it's very difficult to preserve these long-term cooling trends, if they are real. This is because tree rings are wide when the trees are young, and they become narrow when they are aging. This is called the age trend. This is another problem, obviously, but I'm running out of time. And if you do that properly, we thought we did it more properly than people in the hockey stick, then you would preserve this low frequency variability. This is challenging. This is where the differences are, and I will show this now in the concluding remarks. But I want you to take home that higher frequency variations are much better understood than low frequency trends, particularly with regard to tree rings. Now, to the concluding remarks, I will focus a little bit on the IPCC reports doing that. So I'll go through the single IPCC reports. The first one from 1990 showed this picture for the last 1,000 years. So there's a hand-drawn figure. It was actually produced in the 70s. And you see the medial warm period, the little ice age, and then some initial warming after the little ice age. The next IPCC report showed only the last 600 years at decadal resolutions. Smart people at work here. So they understood that at large spatial scale for the northern hemisphere, there's not enough data to really go further back in time. And then there was the third the report that showed then what is called the hockey stick. It was also shown earlier, and you made the point that some of this might be real. We can discuss it maybe later. That is actually, this red curve is the blue curve here, and we made the argument that many of the wiggles are real, like the high frequency wiggles, but the long-term trend that we might have more variability, more temperature amplitude over the last 1,000 years. And I would not say as a result, but if you now look at the newer reports, the one from 2007 and then the one from 2013, I'm showing this as a big picture now. This is the 2013 this year. Then you have this, what we call a spaghetti plot. So these are all northern hemisphere temperature reconstructions from tree rings, but then also incorporating other proxies, of course, multi-proxy based reconstructions. And we see that the temperature amplitude is absolutely different among these records. So one of the records is, one of the light blue ones here is only cooling by 0.4 degrees, and others are cooling 1 degree. So this is where we are right now. So this is from the last IPCC report. I want to point to my colleague who's sitting in the back. He's reading his emails. Jörg Luderbacher is here, so he's the lead author of the chapter. Whatever I'm going to say, blame him. So he did it. No, but they just take what is in the literature and put it together as good as possible in the IPCC reports. But I'm now quoting it, and if you have questions about the IPCC, I will just refer to him or other people that work on the report and also in the audience here. I didn't. Okay. So I would say that these features, the late antique little ice age, cooler here, the medial warm period here, the little ice age here, and recent warming, this is most, if not all of the reconstructions agree on this pattern. The long-term trends, no, I would say they are different. So there are periods where some records are increasing and others would decrease over hundreds of years. So long-term trends, at least for the last 2,000 years, or let's say the last 1,500 years, this earlier period, they're not very well understood. Especially during the medial warm period, maybe Johannes will point to this later, to put this together with the forcing, that is still very challenging, also from the climate reconstruction point of view. And as said, the temperature amplitude. So how much cooling did we have at large spatial scale at the northern hemisphere? Is it 1 degree at decadal resolution when you smooth the curves like this? Or is it only 0.4 degrees Celsius? We just don't know. And it's obviously very important. So I would say before the 1400, we are into the dark. We are losing it. We don't really know how much warmer it was here compared to here, how it is spatially in certain regions. And the point I want to also make here is that there is data overlap. So these are not independent records. These records look very different, even though all of them use tornatores, for example. So there's lots of data overlap, and still they are very different. That might tell you why I believe that before 1400 we really don't have enough data at large spatial scale to say something more precise about temperatures. I spoke about the individual uncertainties. They are neglected here, and you have to, because they're not even taken into account in many of the site reconstructions. So what does the IPCC do about it? What did Jörg do about it? So here's the quote from the Summary for Policymakers. In the Northern Hemisphere, the period 1983 to 2012, so this 30 period, was likely the warmest 30-year period of the last 1400 years. That's what they conclude. This is medium confidence. Medium confidence is 66% probability, so that's not really a lot. You know, chance is by 50. So that this is a very honest report. But we should not believe that it's better understood than it is. It is really not very well understood. So that brings me to the question, and now I'm really making it to the end of the presentation. Why do many colleagues or lots of people believe that the climate of the past millennium is understood, whereas I'm now saying it is not very well understood prior to 1400, for example? And I think this is also an inconvenient truth. I think the person to point to is myself. It's us. When we publish, we have to polish the papers. And we may have a tendency in our papers to over-polish, to say, it's so good, now please make it through the review process paper and don't cause too much trouble. And that, I think, is part of the truth. So we are selling our results better than they are. And everybody does that a little bit on certain scales. And as a sum, there is a belief that it is much better understood than it is in reality. That's one reason. And there's a distinct second reason I want to point to. I think the game changed in 2007. That was really big to the global change community because the Nobel Peace Prize, went to the IPCC and to Al Gore. He produced this movie, The Inconvenient Truth, that was then in the theaters in 2007. And I think since then, there's a change in many people's thinking that, yeah, the climate of the past, at least for the last 1,000 years or 2,000 years, is very well understood. We have to move on. We have to now look more into the future. We have to think about how to mitigate, how to adapt. And that's all correct. But what is not correct is that we understood the climate of the past. That's the point I want to make. And I think that was a game changer, this very important and very crucial event. So to sum it up, I think the knowns, I list some things under the knowns. So interannual to multi-decadal variability over the last millennium is very well understood. The problem is more to the low frequency variability. You need many trees, but the explained variance is still less than 50% is a take-home message. There was a large eruption, and that was in 1452, not in 1458, as far as it comes to the climatic fingerprint of this event. Some of the unknowns I mentioned: low frequency temperature variability, particularly before 1400. That is a big unknown from my point of view. Large-scale temperature amplitude, I made that point. And then later we will see talks. This is then complicating the attribution of forcings, or the attribution of variability during the medieval warm period. And I only spoke about temperature today. It would obviously be interesting to speak about precipitation, drought, clouds, and reconstruct that. So this is the most simple parameter. There are many other parameters that are very important that we have no really good reconstruction at the northern hemispheric scale, not to speak of the southern hemisphere. Thank you for your attention.